All right, I will begin with a word of prayer. Heavenly Father, we thank you for this day. I just pray that you'd help this video to serve the role that class would have today, and I just pray that we'd all understand together, Lord. In your name I pray. Amen. So my apologies in advance for any spurious piano practicing and or music of another nature, sound of outside bugs, the neighbor mowing the yard. Who knows what's going to happen? But hopefully we'll just do math. Anyway, so this is lecture 4, if you're counting, which is on monoids. Now section 2.1 in Nicholson is actually labeled binary operations, which is the first thing I'll define. So a function, all right, a function from the Cartesian product of m to m, m with itself to m, is called a binary operation on the set m. So basically this is just a way of taking in a pair of things and outputting a single thing in the set again. So, oh, I forgot to write, you might write it like this. So we have a comma b, and it maps to a star b for the moment, and that's assumed to be a single thing. This is a binary operation. It's a single way of assigning a particular object in the set M from a pair. Now we have some special terminology for particular kinds of binary operations. For example, if a star b is b star a for every pair in M, then it's commutative. By the way, if there exists even a single pair such that it doesn't commute, if you can find a single a and b such that a star b is not equal to b star a, then it's said to be non-commutative. All right. Now, if we have that, the order, like basically this says parentheses don't matter for three things, right? I can write a star b star c without ambiguity, but then in other words I can either multiply b and c first, or I can multiply a and b first. Now I just said multiply, right? But maybe I should say operate for the moment, because this might be a multiplication, it might be addition, it might be something else. We'll see in the examples momentarily. Then we also have, by definition, if there's an element e in M such that e star a is equal to a, which is a star e for all a in M, for all points in the set we're talking about, then that's called an identity or a unity. And I would add to this that in this case we say M paired with this operation star is unital. So I use this term unital to refer to the property of having an identity for the set with a binary operation. Okay, our first theorem. If a binary operation has a unity, then it's unique. This is actually pretty easy to prove. So e and e prime are both elements of M, so by definition we have e prime equals e prime and e prime equals e prime e, right? Because again, e is serving the role of an identity, so it satisfies this in the particular case that a is equal to e prime here, right? Sorry, use the right pointing. But on the other hand, if e prime is the identity, then we can take a equals to e in the definition, right? And it gives us this. But you notice that e prime e is equal to e prime e, which means that e prime is equal to e. So there you go. The identity, when it exists for a binary operation, it is excuse me, unique. So that brings us to our next and probably central definition of this lecture, which is that, let's get up here for a second, a set M, ignore this for the moment, a set M is called a monoid if M has a binary operation star, which is associative and unital. If star is also commutative, then M is a commutative monoid. All right? So monoids, by the way, guys, it's like a step on the way to saying what a group is. We'll learn by the end of this lecture that if you take a monoid and you add one sort of overarching condition on it, then you get a group, all right, which is what we're primarily studying the next few lectures. Well, about half the course. Anyway, so some examples of monoids. First of all, if you take the usual, oops, my lecture is showing. Fix that. Oh, gotta get another cover paper here so we can focus. What on earth? Sorry, I'll try not to be distracted by the neighbors making unusual noises. Example 1, the usual numbers, integers, rationals, reals, complexes, modular arithmetic, Zn. These are all commutative monoids, either with respect to star being taken to be addition, in which case the identity is what we call 0, or multiplication, in which case we take the identity to be 1. Okay, fine. If you want to be a stickler for the bar notation, you could say 0 bar, 1 bar, and Zn. But as we discussed, we're trying to free ourselves of that pedantry. All right, so next example. If we take real matrices, so Nicholson is fond of using real matrices as an example. N by n real matrices, these are monoids. It's a monoid under either addition or matrix multiplication. For addition, of course, the identity is the 0 matrix. For matrix multiplication, the identity is the identity matrix, right? Now, I would add to this that you could also look at n by n matrices over S, where S is either the integers, the rationals, the complexes, or the Zn. Now, Nicholson, for whatever reason, doesn't feel led to add that set of examples, but we really should, because we can define addition and multiplication of matrices in the same way we usually do for real numbers for any of these sets. All right? So I'll keep coming back to that as an added example to Nicholson. Example 3, excuse me. Example 3 is that if we take, now sorry, my paper's a little bit yucky here, but basically just take a non-empty set. If we had class right now, we'd be talking about the empty set, but haha. So anyway, if we take the power set, in other words, a set of all subsets of M, then this forms a monoid, either with respect to union of subsets or intersection of subsets. If you want to take the union of a set with another set and get back the set again for all sets, what do? You take the empty set, right? The empty set serves as the identity under union. On the other hand, if you want to find the identity with respect to intersection, what you would want is that, A intersect the set, it gives you back the subset again. So if you just take the identity to be the set itself that we're talking about, then that would give you an identity under intersection. So again, the empty set for union, the whole set we're talking about for intersection. And so this is kind of an interesting example. One of the other things you can prove in here is that if you take anything in M, like say A, and look at A star A, you get back A again. I think that was it. Yeah, I think A star A is equal to A for any A in there. All right, enough about that. Let's move on. Move along here. Let me got a couple more examples here. Make sure I'm on frame here. All right. So example 4. Sorry. Focus here. Example 4, Sn, in other words, the permutations we just got done talking a little bit about, and I'll talk about more tomorrow if you come to the help session. Sn is a monoid with the identity permutation as the unity. It's non-commutative for n greater than or equal to 3. Let me show you exactly why that is. It's very simple. If you look at the transposition 1, 2 times the transposition 2, 3, and compare it to 2, 3 times 1, 2, well, 1, 2 times 2, 3, if we start with 1, 1 goes nowhere, 1 goes to 2, then go 2, 2 goes to 3, 2 goes to 3, right? 3 goes to 2, 2 goes to 1, so 3 goes to 1. So we have this in array notation for the left-hand side product. On the right-hand side product, if I start with 1, 1 goes to 2, but 2 goes to 3. I go 2, so 2 goes to 1, but 1 goes nowhere. 3 goes nowhere here, the 3 goes to 2. So you have this permutation. As you can see, this and that are not the same permutation. Consequently, these two elements do not commute, and those two elements can be found in any set of permutations provided that n is larger than or equal to 3. Remember our convention that we can either view 1, 2 as a permutation for n equals to 2, or n equals to 3, or n equals to 4, or n equals to 5, and so forth and so on. Of course, that's an abuse of notation, but it's one of the abuses of notation which makes cycle notation pretty. Now, example 5, we have X not empty, a non-empty set. We can look at the set of all maps on that set. I would sometimes call this the function space from X to X, or if you like, just functions of X. In this case, the composition of maps gives a binary operation on M, which is associative, and the identity is exactly the identity map. All right. Now, in Nicholson, he says that if the size of the cardinality of the set is larger than or equal to 2, that m is non-commutative, but I don't see that. I mean, I think you need the size of the set to be larger than or equal to 3 for exactly the thing we were just talking about over here. So I don't follow him on that. Now, if you can show me why his example, why this comment he has about cardinality of the set being larger than or equal to 2 causes the set of maps to be non-commutative, I'd be interested in seeing it. Maybe I'm just not seeing it, you know? It's possible. Example 6. All right. Example 6 here, let me pull it up a bit. Oop, oop. All right. Is finally a non-example, so to speak. It's not a monoid, in fact. And let's see here. So the definition given for example 6 is that n star m is n to the m for natural numbers. Now, you got to remember that n for Nicholson includes 0. So I guess, I don't know, I'm torn, guys, whether or not I should adopt that notation for this semester. I don't usually let 0 be an n, so it's going to create cross-course confusion for my classes if I let 0 be an n. But of course, if I've copied this out of Nicholson, it's understood that n is including the 0. So anyway, I don't know what to do about that. I can't, you know, I'm bad with making decisions. Anyway, so here we go. It's kind of funny. 2 times 1, or 2 star 1, I should say, is 2 to the 1. But 1 star 2 is 1. So as you can see, it's not commutative. If you look at 1 star 2 star 3, with either doing 1, 2, or 2, 3 first, you get 1 either way. I was like, oh, that's lucky. And then I tried 2 stars 2 stars 2, right, with either 2, 2 first or the 2, 2 last. And again, I got 16 both ways. That was just a quirk of fate. If you look at 3 stars 3 star 3, the one way you get 27 cubed, which is actually 3 to the 9th. If you do it the other grouping, you get 3 to the 27th. These are, of course, not equal. You know, as you're studying these things, you can talk about a departure from associativity, which still holds just for the element being repeated. That's called power associative. It's like power associative would mean that a to the n is defined sort of without order of bracketing. But here, even a single element, you know, operated on successively times itself, you know, gives different results for different bracketing. So this is kind of an awful. Well, I don't know if it's awful, but it is definitely not a monoid. Definitely not associative, nor commutative. Is it anything? I don't know. Something. All right, moving along. 3. So I should talk to you guys about notation. There are. We'll customarily use star and e for the identity, and that's try to emphasize the most abstract things we can say about binary operation. We use this sort of generic. You might say multiplicative notation. Let me put that back in frame here. So, sorry if I was out of frame last time. Anyway, so so this is just sort of a generic notation, but there's 2 sort of common things that happen. The one is multiplication, right? So multiplication, oftentimes we use a special notation. Rather than writing a star b, we write just ab, right? This is called juxtaposition right here. AB, just put them next to each other, that indicates that multiplication is made. So the definition of a monoid looks like this in multiplication, the juxtaposition notation rather. AB is an M whenever A and B are an M, so it's closed under multiplication. There exists 1 in M such that A1 is equal to A is equal to 1 times A. So this is the multiplicative identity of 1. Associativity looks like this, right? No stars. Multiplications do not need to be commutative. If it is commutative, then we have A times B is B times A, right? Now, as a point of habit, I sometimes will say times or multiply for an abstract group operation, and sometimes maybe I shouldn't say that. Sometimes I should say A star B or A operate on B or something like that. So this is, you know, this is a bad habit I have, and if I fall into it in an abstract discussion, you can call me on that, and I'll try to clarify it. But oftentimes we have a multiplication example, and it's helpful, and it's in fact healthy to use the usual standard notation for such an example. On the other hand, there's another class of examples we have, addition, right? And so addition, we write a plus b in the place of a star b. Here the identity is 0, right? Or 0 sub m for emphasis. We must insist that the sum of two things, or a plus b, is in M again whenever a and b are in M. It's closure under addition. There has to be an additive identity, which we call 0, like this, right? And associativity under addition looks like the following, right? Now you guys have all had linear algebra, so these things are familiar. You recognize this as part of, part of the song and dance we give for what it means to be a vector addition, right? It's kind of like this. There's more bells and whistles there, of course, but addition. Now, I would add this. This Nicholson doesn't say, but I would say, is that if you use additive notation for an operation which is not commutative, you're being weird. It is customary in abstract algebra that when we talk about addition, we talk about a commutative operation. So if you want to communicate to the reader that your operation is commutative, then addition is a good choice of notation. Now, if you're just trying to be obtuse and hide what you're doing, then by all means, use star for an addition. Okay, now, I will try not to be too obtuse with you, for the most part. Cayley table. Cayley table is a nice way to indicate a finite set of products for a finite set. In other words, to define a binary operation. Here's a good one. So here's the set we're looking at in this case is M. Let me say M is the set containing E, A, B, and C. All right. Now, so the first row and first column here, you can see what those mean is that E times E is E, E times A is A, E times B is B, E times C is C. A times E is A, B times E is B, B times C is C. Let me just write that down here again. So like this one right here, that is C times E equals to C. Whereas, let's say this one right here. This one is E times B is equal to B. Okay, that's the order in which you read these things. Here's a few more examples. A times B is B is in green. A times B is B. On the other hand, B times A is B, the purple, right? 2-3 spot versus 3-2 spot. I'm not counting these as labeling column and rows, right? All right, fascinating. But I mean, this is a nice notation for, telling 16 different possible things without writing out 16 sentences. So it's a nice, I guess, introduced by Cayley back in the mid-19th century. Certainly not his greatest accomplishment, but one of the many. Now that if you look at this, sorry guys, if you look at this, you can notice that across the diagonal here, we have A with A, B with B, C with C, B with B, E with E, C with C, and then the diagonal is whatever it is. But this is a commutative binary operation because, as you can see, A times B is B times A. Well, I'm using A and B as variables. That's probably bad. X times Y is Y times X for all X and Y. It would probably be a better statement here, since A and B can't be variables, as they have a fixed and particular meaning here. Shut up, bugs! Sorry, I can't make the bugs shut up. They will do what they do. Okay, so, anyway, this is a commutative binary operation. It's not a monoid, though, because it's not associative. Here's an example. If you look at A times B times C, it's not equal to A times B times C. With appropriate grouping, right? Multiply BC first, we get E. Multiply AB first, and then C last, we get C. These are, of course, not equal. By the way, this is example 7 in Nicholson, but I added ugly stars. He has used juxtaposition for his example, which means that he's, well, wiser than I am, but you already knew that. All right, so finally, we get to something that has a little more substance to it. Generalized associativity. So the neat thing is, if you have associativity, right, of 3 things, you can just as well have associativity of 4, 5, n things. So here we go. Let A1 through AN be elements of a monoid. If the product A1 through AN is formed by successive multiplications, and this is kind of important in that order, in other words, that A1 comes first, A2 comes second, and so forth and so on, all the way out to an. I mean, you might multiply a1 and a2 first, and then multiply everything past it, but the ultimate product is in this order, all right? Then the result is independent of the bracketing used. Now, I think if you go to, so let me just kind of go through the proof of that with you. I'm going to write this one out because I think it's a little bit important to see it. So here it is. So the proof, we begin by developing a sort of standard notation. We'll say that, and I'll follow Nicholson here basically, that a1, a2, dot, 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 an is the standard product in that order. All right, defined inductively as follows. So first of all, if we just have a1, it's just a1, all right? And then if we have a1 through an, well, that's defined to be a1 times a2 through an, all right? For n greater than or equal to 2. So for example, if we look at a1, a2, by definition that's a1 with a2, which is a1, a2, right? Or if we have three things, we can take a1, a2, a3, which is a1, a2, a3 by the recursive definition, which is then a1 times a2 times a3, right? Etc. All right. So what we're going to do is we're going to use strong induction to prove that any product of a1 through an in that order can be rewritten as the standard product, right? So any product P of a1, a2, dot, 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 an has, let's just say P equal to the standard product of a1, a2, dot, 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 an. So in other words, we're using this standard product as sort of an anchor. Any other possible bracketing we're going to prove can be put back to the standard product. In other words, this bracketing. And so we have the fact that we can just erase bracketing, and we can be assured of the generalized associativity of the product. In other words, we don't need to write parentheses for products in a monoid. All right, but this is for n greater than or equal to 1. So the induction is going to be on the number of elements in the product. All right. Now, so to begin with, we should notice that P is clearly true for n equals to 1, n equals to 2, and n equals to 3. Now, n equals to 3 is actually just the standard associativity, right? So let's assume, so clearly, I'll just write that, clearly P equals to a1 and P is equal to a1, a2, and P is equal to a1, a2, a3 by definition of monoid and the notation, right? So suppose inductively, by strong induction in fact, that the result is true for a product of n things, right? Let's see here, make sure I got my MOAs. See, by strong induction, that the induction hypothesis. Suppose by strong induction, the induction hypothesis is true. Any product of n minus 1 or less elements in a monoid can be written in the standard bracketing. In other words, suppose that the order of brackets doesn't matter for any product of n minus 1 or less elements. So we want to consider P formed by n of them, right? Because we'd like to show that it doesn't matter how we form the brackets. P formed by product of A1, A2, an in that order. All right. So there has to be some sort of, outer product, right? We have to be able to write P equals to Q times R. So where, Q is formed by the product of A1 through AK. In that order, and R is formed by the product of AK plus 1 an in that order, right? There has to be, some last multiplication, and we're saying that that last multiplication happens between these products of the Q and the R, right? Here, of course, 1 is less than or equal to K is less than or equal to n minus 1. So, excuse me. Notice if K equals to 1, then we're done, right? Because what's P? P would be equal to A1, and then the R would be A2, an, right? Which by definition is A1, A2, an. So we've shown that if K equals 1, then we can rewrite the P in terms of the standard product. Now, on the other hand, if K is greater than 1, then what do we have? Now, oh, by the way, I'm sorry, I should emphasize, how did I know that this can be R? How did I know I can put R into the standard bracket of n minus 1 things? Oh, n minus 1 things, right? So this is by induction hypothesis that I can rewrite R. If R is not already a standard bracket, then I can rewrite it as a standard bracket by the induction hypothesis because R is formed by the product of n minus 1 things, right? Now if K is greater than 1, then we can both Q and R are, of course, products of less than n things, which means they can be both put into their standard bracket by the induction hypothesis. Now oh, I'm sorry, I'm pretty off the screen now. I'm so sorry. Nope, not yet. Hooray. So let me just try to complete this argument here and get on with our lives. So, sorry, I'm kind of running out of room here, but I think I can fit it in this last line. So if K is greater than 1, then we can write Q is equal to A1, A2, AK. How can I do that? Because remember that K is at most n minus 1, so by induction hypothesis I can rewrite it as a standard bracket, and then by definition of standard bracket I can rewrite A1 through AK as A1 times A2 through AK, right? And R is equal to, well, again, by the induction hypothesis, AK plus 1, an. So P is equal to QR, right? But that's A1, A2 through AK, right? Times what? Times A K plus 1 through AN, all right? And then by what? By associativity, right? This is A times B times C. That's the same as A, which is A1, times B times C, right? But again, by the induction hypothesis, we have a product of n minus 1 things, so we can rewrite that as the standard product, right? And then by definition, that is the standard product of the n things, and there you go. Whew. Well, it took us a few minutes, but it was worth it, because now, whenever we're working in a monoid, we can be rest assured that we don't need to put in parentheses, right? We can just talk about the product of a1 through an without ambiguity. And that is a good thing. All right. By the way, this is also one of the reasons that we're using Nicholson and not Galilean, is because, as far as I remember, this is not clearly done in Galilean. The other thing that's kind of a little bit, I was a little bit perplexed by in Galilean was exponent laws. They're not quite as clearly, I mean, Nicholson doesn't have the complete proof of the laws of exponents either, but there's a reason for that. They're a pain. All right, but he does at least have a proof of the basic laws of exponents. So first of all, what's the definition? What do we mean law? What do you mean laws of exponents? What are you talking about? All right, so let's talk about it. Here's the definition. If A is an element of a monoid, and excuse me, A is an element of a monoid, and so n is either 1, 2, 3, or 0, ... Then the nth power of A we denote by a to the n. A to the 0 is understood to be 1, where 1 is the multiplicative identity, right? So you might say a to the 0 is e, if you're using that notation. Sorry, I'm using the proper pointing here. And then recursively we define a sub n, a to the n rather, as a times a to the n minus 1 for n greater than or equal to 1. So that's power. Positive power, right? Integer. Excuse me, natural number power, according to Nicholson. All right, anyway. So here's some properties that we should be aware of. A to the n times a to the m is a to the n plus n. A to the n to the m is a to the nm. And if a and b commute, then we get a b to the n is a to the n b to the n. Now, if a and b do not commute, then this is not true. Okay? Just warning. You should know that from linear already, but, Great. Now the proof of these is pretty easy. We fix m greater than or equal to 0. And to prove 1, we work by induction on n. For n equals to 1, a times am is a to the m plus 1, but I'm an idiot. I suppose the induction start at 0, right? Sorry. So a to the 0 times a to the m is 1 times a to the m, which is a to the m, which is a to the 0 plus m. So there you go. There's n equals 0 step. And then if we assume inductively that it's true, for n greater than or equal to 1, if you look at, and these proofs aren't worded quite right, my apologies, it was late when I wrote this, but anyway, I assume that you could all write a nice and carefully worded proof here. I'm hopefully not overstepping my bounds there, but anyway, a to the n, a times a to the n minus 1. If you ask me nicely in the help session to give a concise and completely correctly worded proof of this, I'd be happy to do such. Maybe happy is too strong a term. But anyway, a times a to the n minus 1 is that by the definition. And then here, well, that's n minus 1, so by induction, strong induction, I can do that. By associativity, I can do that. Then by the induction step, I have this, but then by the definition of product, I can get n minus 1 plus m plus 1. Technically, I'm supposed to add the... Anyway, let me shut up. So there we go. A to the n to the m is a to the 1's cancel, m plus n. And that proves the induction. So 1 is true, for any m and n. And the induction for 2 is not much different. It's a little bit different, I suppose, but let's see here. I'll move this up a bit. Come on. Come on. So if we fix n greater than or equal to 0, use induction on m. Again, for m equal to 0, it's true. if we suppose that a to the n to the m is a to the nm for m greater than or equal to 1, then if we look at, I decided to look at m plus 1 for a change. Anyways, so broken from, so it seems like Nicholson usually assumes n minus 1 is true and then proves it for n. My habit is to assume it for n and show n plus 1. In this case, m plus 1, m as in mummy. But anyway, this would be, by definition, that, right? Which would be, by inductive hypothesis, this, which would be that by part 1, right? And then that's m plus 1n, so there you go, by induction. Now, part 3 we're leaving as an exercise. It's exercise 10, so I'm going to go on. I think it's probably worth me taking like a minute of your time. Ah, curses. I knew somebody was going to start mowing their yard. Well, we had some good time. But anyway, here we go. I have stuff to talk louder. So Theorem 2, in additive notation, looks like this, right? In other words, you can write addition without brackets. A1, sum of A1 through AN is the same no matter how you add it, either whether you add the first one and then the last n minus 1 of them or whatever. Addition is associative and true for true for 3 things, true for n things. Theorem 3 is a little bit more interesting. In additive notation, a to the n becomes na, or sometimes I'll write n times a, just to be a little bit more clear about what's going on here. N times a means to add a to itself n full times. We could define this more precisely over here, like 0 times a is 0, 1 times a is 1, and if I have n times a, oh, 1, what? Come on, dude. Man, good grief. There we go. Sorry, it's just all this partying I've been doing the last day. It's got my mind all twisted. And, it's a joke, mostly. N times a, well, that's the worst possible person mowing. That's my direct neighbor. Curses. N times a is equal to a plus n minus 1 times a. So in other words, add one more to the n minus 1th, to the sum of n minus 1 of them, right? So that would be additive notation. And in that notation, Theorem 3 looks like, goodness gracious, it's like the apocalypse of noise here. N times a plus m times a is n plus m times a. And m times, this is what Theorem 3, the laws of exponents, look like when we look at the additive version. So it's kind of neat. Just I think it's worth saying that because, monoids are sort of abstract. They're not sort of, they are abstract objects, and we should appreciate sometimes what these theorems that we write in a multiplicative notation would look like if we wrote them in an additive notation, because you might be surprised that that's actually what we just proved. Well, I proved this and that, but I technically haven't proved that because I relegated it to an exercise. All right, moving along before it gets louder. Yeah, sorry. Inverses. Inverses. What are inverses? Well, if A is a monoid, and B is an element of M such that A times B is 1, and B times A is 1, then B is called an inverse of A, right? In the additive world, we would have that A plus B is equal to 0 and B plus A is equal to 0. And in fact, we would call this B would be called the inverse of A, right? Whereas here, B would be called the multiplicative inverse of A. Although sometimes we'll just say the inverse of A when it's clear from context. We say that an element A of M possessing an inverse is a unit in M, all right? And let me just, main theorem here. If M is a monoid and A in M has an inverse, then that inverse is unique. So that's pretty awesome because that means that we can write without ambiguity that B is equal to A inverse for the multiplicative case, or B is equal to minus A for the additive case. And again, as I told you, that's called the negative. The proof that an inverse is unique is pretty simple. Here it is. Suppose we have AB is equal to 1 and BA is equal to 1, and also AB prime is equal to 1 and B prime A is equal to 1 for some B, B prime, and A and M. In other words, both B and B prime are playing the role of inverse to A. Well, then we can play this game. B is B times 1, but 1 is AB prime, right? And AB prime is, what is it? Well, associativity, right? That's BA times B prime, but BA is 1. And 1 times B prime is B prime. So there you have it. B is equal to B prime. The inverse in a monoid is unique. Hooray. Some examples. First of all, if we're dealing with the additive, make sure I'm on frame here. If we're dealing with the additive monoid, Z, the reals, the complexes, Z mod n, n by n matrices over the reals. Again, this, assuming the matrices over the reals is not needed, you could let this be this, any of these, right? N by n matrices with any of our favorite number systems, still in fact, a monoid with respect to addition. And yes, it's true. Every element of these monoids is a unit, and each element has a negative, which we call minus x, right? So in other words, there's always an additive inverse for everything in these guys. In contrast, if we look at, I'm trying to, not very good at multitasking here. If we look at the reals with respect to multiplication, or the complex numbers with respect to multiplication, every non-zero element is a unit, and of course 0, the inverse of 0, does not exist. Alright, so that's in fact, I'll tell you the secret, these are fields. This is in fact going to be the definition of a field much later, is that we have a, well, it's a little bit more than that, fine, I'll shut up, but anyway. That's symptomatic of the fact that R and C are fields. Everything non-zero has an inverse. A little bit more to it than that, but that's the main point. And if we look at the integers with respect to multiplication, we have units of plus or minus 1. We touched on that the other day in class. And I mentioned to you guys in class also that Z and Zn, everything's either 0, a unit, or a zero divisor. A sort of a counterexample to that, well, not a counterexample, but an example of a ring where you've got more than just units and zero divisors, and 0 would be the integers, right? Because if you look at 2 in the integers, right, is it possible to have 2 times, can you have 2 times x, where x is an integer equal to 0, and yet have x be not 0? Well, no. I mean, there are no zero divisors in the integers, and yet 2 is not a unit, because you can't solve this equation. You can't solve 2 times n equals to 1 with a integer. Or you need a half. So the integers are such a thing that there's more than just zero divisors, 0, and units. Just a thought. Okay, moving along. Almost done here. Example 11, I thought it would be nice to give you some gory details. The units of Zn are the residues A bar where GCD of AN equal to 1. I don't know if that's a flea or what, but I want to get out of here. Get out of here. Scoot. Again, I'm sorry. I had to write A bar here so that this would be sure to make sense. I mean, I could write A here and here if we understand each other, that this would be a set of integers, whereas this is, of course, a comment about integer arithmetic, right? The greatest common divisor of A and N. I have not defined the greatest common divisor of a residue class and an integer. I'm not sure I want to try either. Okay, anyway, so this notation, right, oops, I'm sorry, I was off frame. Notation Zn star, this is notation, what this means is it's the set of units in Zn, all right? So the other help session, we noticed that n minus 1 squared is n squared minus 2n plus 1, which is congruent to 1, right? Which means that in Zn, n minus 1 is always going to be a unit, such that it's its own inverse. And I actually kind of like just show a few examples of that happening down here. But just to read it off, the units in Z2, just 1. Units in Z3, 1 and 2. Units in Z4, 1 and 3. See, because 2 is not a unit, because 2 times 2 is 4, which is 0. Right? 0 is never a unit. Z5, 1, 2, 3, 4. That's the units in Z5. Z6 has got 1 and 5, right? 2 is out and 3 is out because 2 times 3 is 0, which means neither 2 nor 3 can be have multiplicative inverse. In 7, we get 1, 2, 3, 4, 5, 6. In Z8, these are the numbers relatively prime to 8. Those are the ones with inverses, right? So like, but again, like 7 times 7 is 49, which is 1 mod 8. So 7 is its own inverse, like 7 is equal to 7 inverse. I didn't write it down. 8 times 8 is 64. 64 is 1 in Z9. 8 is equal to 8 inverse. That means no accident, all right? But anyway, I thought it might be helpful for you guys to actually see them explicitly. These are the numbers which are relatively prime to n for each one, and these, of course, also precisely the residues which have inverses. And we will soon learn that these form a group. Each one of these is in fact a group because, well, I'm getting ahead of the story a little bit, but in fact, groups. Oh, did I get to the bottom? Yeah, okay, cool. Example 12, if we look at the set of maps under composition, then the units in this monoid are the bijections. All right, bijections are mappings which have inverses, right? That was Theorem 6 in Chapter 0, some section. I forget which section, but anyway. It's got an inverse if and only if it's onto and one-to-one. We're talking about a map on a set, right? So the bijections are exactly the ones that are units with respect to function composition. I said that the permutations of X was their collective name, right? That's the set of all bijections of the set X. So if we use this notation, take a monoid, put a star on it. This monoid with a star on it is the set of all things in the monoid which have inverses, right? So with respect to this notational choices, the permutations of X are M star, where M, of course, is the set of all mappings on X. In particular, if we look at the set X equals to n sub n, in other words, numbers 1 through n, 1, 2, n, then M star is in fact the set of permutations, or Sn, this so-called symmetric group. Whatever a group is, I'm sorry, it's killing me. Next class, won't be long. Another example, if we look at n by n matrices, the units are the invertible matrices, which we know and love from linear algebra as being the matrices that have determinant non-zero. That's the condition needed such that there exists, right, B in MNR with what? Oops, sorry, I'm about to write determinant again. AB equal to I equal to BA, where this I is, of course, 1, 0, 0, 1, 1. I'm sorry, what am I saying? Ij is equal to delta ij. There's a better definition for you. The identity matrix, anyway. So if the determinant's non-zero, it's an invertible matrix. We know it. We love it. But by the way, I should mention that, that all that wonderful real matrix arithmetic calculations serve equally well to define invertible matrices of real, complex, integer, or even modular integer entried matrices rather. And in fact, you can again prove through much the usual arguments that it's going to be an invertible matrix of these sorts of things if and only if the determinant is a unit in these objects. Now, of course, to say that the determinant's a unit over R or C is simply to say that it's non-zero. To say that the determinant is a unit in Z means that the determinant of A is plus or minus 1. So if you have a matrix of integers, if you want it to be invertible, you need the determinant is plus or minus 1. And I say invertible in the universe of integer arithmetic, right? You're not allowed to take fractions. In Zn, you have a matrix in Zn. It's going to be invertible provided the determinant is in the group of units of Zn, which we just got done talking about. So this is a much larger class of examples, which Nicholson doesn't seem willing to talk about at the moment, but I will talk about it because they're interesting examples and we should be aware of them. Okay. Finally, and I won't go through the proof of all these, I'll just do like maybe 2 really. Well, I guess 1, 2, 3. But these are properties of inverse. First of all, the identity is its own inverse. Yay. If A is a unit, A inverse is also a unit. The inverse of the inverse is the element again. If A and B are units, then AB is a unit. And we have that AB inverse is B inverse A inverse. Now, I think you guys already know this because you've had linear algebra, but this is the so-called sock shoes identity, right? Because you multiply AB. In other words, if you put on your socks and then you put on your shoes, then to undo it, you gotta first take off your shoes and then take off your socks. At least for physical feet and physical shoes and socks that I'm aware of anyway. But so, and then of course we have the n-fold, so the socks, shoes rule, and then also the fact that if we have a to the n, then the inverse of a to the n is the inverse of a to the n. Sorry about that. English is what it is, but there it is. This, of course, 5 is just nothing more than 4 with a1 equal to a2, equal to an equal to a. So let me look at the, well, I mean, the proof of 1 is just that. The proof of 2 is also just basically by definition and staring. 3 is a little bit more interesting, and I was chastised last year for just proving it and not explaining it. So I'm actually going to try to derive it here right quick. Suppose A inverse and B inverse exist, right? Well, what should the inverse be? So, like, solve it, right? If there is an inverse, we should be able to solve this equation. Multiply on the left by A inverse, you get A inverse times 1 is A inverse ABX, but, you know, by associativity, we get A inverse A, but that's 1, right? So we get A inverse is 1 times bx, which is just bx. Sorry, I didn't write down a few steps right there. And then if we multiply both sides by b inverse, you get b inverse a versus b inverse bx, but that's x, right? So, goodness gracious, I guess we probably should try that the inverse is b inverse times a inverse. And so I do that. As you can see, product of AB and b inverse a inverse is by associativity, that, but by definition of inverse, that's 1. Which gives me that, but then again, by definition of inverse, that gives me 1. And the opposite order, again, we get that. So we have the product of this times that, and that times this is both 1, which means that the inverse of AB is B inverse A inverse. And there you go, that proves 3. 4 is by induction, I won't write it out. And again, 5, if we just take A1 equal to A2 equal to AN, we'll get A inverse, which is equal to A inverse, A inverse, A inverse, A inverse, A inverse, but that is A to the n inverse, and the other side is A inverse to the n. So, again, these could be made more rigorous. So, if I asked this on a test, I would hope you gave me a more careful argument, you know, and I would also be probably hoping you spent longer than the 20 seconds I just spent on it right there. Finally, the big picture. Well, I don't know if it's a big picture or not, but our last theorem, if A and B are units in a monoid, then A to the n, A to the m is A to the n plus n, and A to the m, so laws of exponents for units, all right? And if A and B commute, then AB to the n is, now, the difference here between this and our last theorem is now m and n are integers, right? So we're defining negative powers for a unit, in particular A to the n is A inverse to the n for n a negative integer, right? So we define negative integers by powers, positive powers of the inverse. Now, the proof of this I worked out last year, and there's more than you think here, because you got to think about this one being positive and that one being negative. You got to think about this one being negative, that one being positive, and there's like different cases to sort through. They could both be negative. There's nothing terribly difficult here, but there's a lot of cases to keep track of. So the proof is left to the reader. And again, I have some proof written out. It's awful. It's like 3 stupid pages of just the argument we already went through for the positive case, but a little bit of nuance there. All right, finally, getting to more. So the point is we have these laws of exponents to use going forward, okay? So here's the big picture observation. We've looked at different monoids in this lecture. In particular, we looked at like the set of subsets under intersection or union, and those, the only unit was the identity, you know, either the whole set or the empty set. We also looked at the integers under multiplication. There the units were plus or minus 1, right? Again, a very, very small piece of the pie. for modular arithmetic, we had the integers being, all of the elements which were relative residue classes whose generators are relatively prime to n. That's bigger, but still not everything. N by n matrices, they had lots of units, but not all, right? Determinant non-zero had the units. And then finally, the thing we're about to start talking about are groups. And group is this rather special case where all of the elements are units. So, M star, the group of the units in M, it's always a subset of M, but when M is a group, these are equal. M star is equal to M for a group. So that's what we're going to be talking about starting Wednesday, and I hope you could hear me over the lawnmower. My apologies. Anyway, party on. Thanks.